numerical simulation of turbulent flows. This is one of the most important applications of CFD which we would discuss in this module. So, outline of the module, we will have a look at the basic features of turbulent flows, and then we will talk about the numerical simulation strategies which are employed for numerical simulation of these flows. We will look at 2 or 3 strategies, in particular what we call a RANS simulation, which is Reynolds averaged Navier-Stokes simulation, wherein certain parts are modeled and there are various turbulence models which are used in industrial CFD simulations. We will discuss some of those models in this module. We will then take up one of the most promising simulation strategies, specifically with increase in the computational power available to us, what we call large eddy simulation. So, now let us come to the first lecture in this module, wherein we will have a look at the basic features of the turbulent flows, why we need to worry about the turbulent flows, and what are the simulation strategies which are the ones which are employed in industrial CFD simulations. So, outline of the lecture, we will have a look at the features of the turbulent flows, numerical simulation strategies, and then what is referred to as Reynolds averaging procedure, and if time permits in today's lecture, we will also have a look at Reynolds averaged Navier-Stokes equations which are used in our RANS simulations. Now, let us see, why do we bother about turbulent flows? That is one thing. We have learned about many techniques of CFD simulation, but why in particular turbulent flows? What is so special about these flows? And the answer is very simple. It can be summed up in one word: ubiquitous. You look anywhere, all around you, wherever you encounter fluid flow, mass transport or energy transport, the underlying flow most of the time is what is termed as turbulent. So, that is why we say the turbulent flows are encountered in wide range of natural and enduring systems. For instance, we live in the atmospheric boundary layer, wherein the airflow is almost always turbulent, and this turbulent airflow has to be simulated, taking care of the inputs obtained from different weather stations to have what we call long range as well as short range weather focus. Similarly, the flow through rivers or canals, you go to any river side, you will see the flow. If you just observe the flow the way it is taking place at a particular point, at a particular station, you will find it is continuously changing, and there is no pattern of that change. What you will find is the pattern is entirely random, which is one of the most important features of what we call turbulent flows. Similarly, ocean currents, they are almost always turbulent. Flow over the transport system, it could be any land based, sea based or air transport systems. Flow over them is what we call high speed flows. Higher the speed of a vehicle, more prominent would the turbulence be. So, the flow over our cars, our trains, buses, aircrafts, they are always turbulent. So, if you want to come up with a design, good design of an aircraft or a car, we have got to deal with the turbulent flow around it. We should be capable of modeling all its features and the effect it has on in producing the drag, which we would like to minimize in the case of a transport system. Similarly, flow through all types of fluid machines which we use in industry, whether they are hydraulic or gas turbines, pumps, compressors or blowers, all of these flows are invariably turbulent. We can also look inside us, the blood flow in our large arteries, that is also turbulent. Let us go out of our planetary system, let us go out of our environment or Earth, the interstellar space, there are some flows happening which are of interest to astrophysicists. This is also turbulent. The sun flares, what we call solar flares, which affect our life, which affect our communication systems and our energy supply system in a big way, those solar flares are always turbulent. So, that is why we would say this turbulent flows are found everywhere and we should be able to at least get some usable estimate of such flows using numerical simulation or theoretical means, or whatever means we have got, we should be able to get at these flows. So, it is due to this ubiquitous nature and importance in engineering applications and physics analysis, these turbulent flows have received what we call considerable attention from theoreticians, mathematicians, physicists, engineering scientists, you name any, experimentalists of all kind, and numerical analysts over past century, I would say rather centuries. The first study of turbulent flows dates back to many centuries ago, and there has been furious effort in understanding the features of turbulent flow, but sadly it is still one of the what we call unsolved problems of physics. We haven't yet been able to solve it in its entirety. So, the difficult nature of the problem, it still fascinates scientists and engineers alike. So, there is still considerable amount of work to be done using theoretical tools, experimental tools, and CFD tools to understand the turbulent flows around us. So, that is the reason why we would like to take up as one of the most important applications of CFD, the numerical simulation of turbulent flows, and that is the subject of this module. Now, let us have a look at what are the basic features of turbulent flows. In a fluid mechanics class, you might have heard this classification of laminar flow and turbulent flow. Laminar flows are always very nice, layers of fluids sliding past each other in a very smooth fashion. And you might have also heard about the famous experiment of Osborne-Reynolds flow through a pipe, wherein we steadily increase the rate of the flow, mass flow through the tube, and the pattern of the flow changes from being what we call a beautiful laminar flow in the beginning when the flow rate is small, to the appearance of the undulations or unsteadiness in the flow, which might die little later, to the full blown random flow patterns in the tube depending on the mass flow rate, which will later link to a parameter which we call Reynolds number. And what was learnt in the case of pipe flow, that there is certain critical Reynolds number below which the flow would always remain laminar irrespective of the disturbances upstream. Those disturbances will die down and will give us a very smoothly flowing laminar flow, and there is certain range beyond which the flow will always contain any disturbance in the flow which come from upstream. They get magnified and we get a chaotic flow pattern. So, what are these basic features? One thing which we observed, which we learnt in a fluid mechanics class, is the Reynolds number, which is a strong indicator of the nature of the flow. So, higher the Reynolds number, higher is the likelihood of the flow becoming turbulent. But what are other features of turbulent flow? So, let us have a look at some of the prominent features of turbulent flow. The first word which comes to our mind is random. Turbulent flows are highly unsteady. In fact, they cannot be predicted in its entirety. So, that is why we use the term random. A simplest example could be that you just go on, sit down near a river stream, fix your attention at a particular point where you are sitting, and just see the flow pattern. The flow pattern will change in unimaginable ways, which is unpredictable. You go the same time next day, you will find a different flow pattern, though the average flow through the river or the canal would be the same as it was on the previous day, or rather forget about days, just few minutes back, a few seconds back. So, this turbulent flows are highly unsteady or random, and they are always 3-dimensional. There is nothing like 1-dimensional or 2-dimensional turbulent flow. The second most important characteristic is what we call diffusive. This is rapid mixing in turbulent flows. This rapid mixing is of great importance to us in chemical processes where we require a thorough mixing. So, we have in turbulent flows a rapid mixing which leads to increased rate of momentum, heat, and mass transfer. In many of the chemical industries, it would be one of the most desirable features, and when we are dealing with the transport industry, there it was one of the features which you would like to hate, or rather we would try to minimize its effects, because it also leads to increased drag. So, if we are designing a car, we are designing aircraft, we would like to reduce this diffusive effect, so that the drag is reduced on our transport machine. And if you look carefully in a turbulent flow, for example, go and observe, have a look at the way the flow is taking place in a river, what you will find, there are a wide range of structures. These structures, some structures which are very small, some of which are very large, some last for a very long time, they remain almost a similar shape, they retain the shape over a fairly good period of time, and the some which just they arise and vanish. So, that is why we would say that turbulent flows or turbulence contains a wide range of spatial as well as temporal length scales. We will have some structures, vertical structures, which are fairly large, and they would retain their shape for a fairly large time. So, they have got large length scale, or what we call spatial scale, as well as large time scale. There would be some smaller eddies which arise and then they rapidly vanish. So, we would say they have, those eddies have got a very small length and time scales. And if you want to have a complete grasp or understanding of a turbulent flow, we should be able to understand what is happening at all these length and time scales, or all these spatial and temporal scales at the same time, and what is the effect of their interaction. The next characteristic is what we call rotational. The turbulent flows, they always contain a great deal of fluctuating vorticity. You go to smaller length scales and the fluctuation becomes even more random and vigorous. So, this is in contrast to what we used to make assumption, which we used to make in our fluid mechanics class, that if you want to solve a problem away from the solid boundaries, we will invoke the irrotationality assumption, that the flow could be treated as irrotational, and we came up with a scalar potential which we can solve for, and thereby we can obtain the solution of a flow problem. We can get the velocities and use Bernoulli's theorem to get the pressure distribution and so on. But the same thing we cannot do with turbulent flows, because turbulent flows are never ever irrotational. They contain loads and loads of vorticity at different length and time scales. The next most important feature is dissipation. Turbulent flows are always dissipative, and this dissipation comes up because of the viscous action. Now, this is sort of a dichotomy here. We would say that turbulence occurs at high Reynolds number. At high Reynolds number, viscous effects are fairly small compared to the inertial effects, but the losses in the turbulent flows or dissipation, loss of energy, occurs because of the viscous shear stress. In fact, this dissipation is entirely due to the action of viscosity. So, these viscous shear stresses, they perform deformation work which increases internal energy at the expense of the kinetic energy of the fluid, and to maintain the turbulence, basic features of this random flow, turbulence needs a continuous supply of energy to make up for the viscous losses, the energy which is being lost at what we call dissipation scale by action of molecular viscosity. And from where do we get this energy? This energy is extracted from the mean flow by what we call the instabilities, and one of the ways in which it is characterized is what we call eddies, or largest eddies in the flow. They are the ones which extract the energy from the mean flow, and then that energy is cascaded, or what we call passed through, in a hierarchy of eddies. So, we have got, let us say, a pretty large eddy whose length scale might be equal to the dimensions of the flow of interest, and then we have got slightly smaller eddies which are smaller than that and smaller than that and so on. So, thereby we have got what we call a cascade of eddies, and through this hierarchy there is a cascade of energy through smaller and smaller scale eddies, and ultimately there is a dissipation of energy at the smallest scale, which we call dissipation scale. We will discuss these scales in bit more detail little later. Now, as noted earlier, turbulent flows always occur at high Reynolds number due to instability of the laminar flow, and please remember this, though the turbulent flow is random, we talked about various length scales of widely differing magnitude. We talked about some very large length scales which are linked to the largest eddies, and very small length scales where the energy is dissipated due to molecular action. But nevertheless, the turbulence is still what we call a continuum phenomena. So, with the smallest scales which we encounter in turbulent flow, they are far larger than any molecular length scales. So, we are not in the realm of dealing with each molecule separately, we are still talking about the effects at a gross level, what we call a continuum level. And also remember that turbulence is not a feature of a fluid, it is nothing like a turbulent fluid, but it is a feature of the fluid flow. And major characteristics of turbulent flow, they are not controlled by the molecular properties of the fluid. So, you might have the same, the water flowing through different channels, and one channel, depending on the dimensions of the channel and the flow velocity, the flow might be turbulent. In other words, it might be laminar. So, the turbulence does not depend on the properties of the fluid, but it depends on the other features of the flow. Now, let us talk about the scales which we encounter in turbulent flows. We talked about that we encounter wide range of length and time scales in turbulent flows. So, we will have a qualitative description of some of these scales, the way they have been proposed in the literature. We will talk about these scales, and we also talk about the rate of dissipation of kinetic energy, and we will talk about characteristic flow velocity and length scales. And then we talked about what we call energy cascade, which was proposed by Richardson way back in 1920s. So, what is this energy cascade? So, some of these features we are going to discuss in detail, and what we mean by large eddies and small eddies. Okay. So, to understand these, let us go back to our board. So, length and time scales in turbulence. Before we deal with these scales, there is one particular quantity which is very important in turbulent flows, which we call rate of dissipation of kinetic energy. That is the energy which is dissipated at the smallest scales of the motion in turbulent flows. So, can we get a measure of that dissipated energy? So, this rate of energy dissipation per unit mass, and it is very popular in the literature to use the symbol epsilon to denote this energy loss. So, epsilon is given by 2 nu Sij Sij. So, Sij into Sij, we have already been through this tensor. Sij is a scalar product of these of the second order tensor. So, here nu is our kinematic viscosity, and Sij is our strain rate tensor, which, if you can recall, we have defined it in terms of the velocity gradient tensor. So, this Sij was defined as half of del Vi del Xj plus del Vj over del Xi. So, you can clearly see the strain rate in the fluid anywhere, that is proportional to the velocity gradients, and this epsilon, it depends on the product of the strain rate tensor with itself. So, one consequence is very clear, that higher the velocity gradients, higher would be our dissipation rate. So, dissipation is pronounced particularly pronounced in those regions in regions of flow where velocity gradient is large. Now, we have introduced this term that rate of energy dissipation, because one of the length scales, the smallest length scales we would define in terms of this energy dissipation per unit mass. So, this is a first definition. Second, let us say we are dealing with the flow. Now, whenever we talk about a flow that happens in certain situations or certain surroundings, so there would be a characteristic velocity, or sort of you can think of an average flow velocity. So, we will talk about the characteristic flow velocity. Let us denote it by symbol capital U. Similarly, we can also talk about the dimensions, or what we call characteristic dimensions of the flow region. Let us denote it by symbol L. Now, both of these you can easily correlate with what happens in the case of, let us say, pipe flow. In the case of flow through a pipe, U could be the average velocity and L could be identified as the diameter of the tube. Now, based on these two characteristic scales, that velocity and length scale, we can define a Reynolds number or E. Let us put a subscript L to indicate that this is based on our characteristic length scale, which characterizes our flow domain. It could be diameter of the tube, it could be, let us say, width of it or depth of a channel, or it could be the span, wingspan of an aircraft, depending on where the flow is taking place, what is the flow of interest to us. REL is U into L by nu. In turbulent flows, we are particularly interested in what we call large Reynolds number flows. So, turbulent flows, this would happen when this REL is very large. Now, what is this very large? That is, again, it is dependent on the problem. The definition of the large, there are in different situations we have got different limits on what we call critical Reynolds number when transition from laminar to turbulence takes place. Okay. Now, based on, now these are few defining things for us. We have got this Reynolds number and we have got our characteristic velocity and length scales, and then next we are going to talk about what we call ADs in our Richardson energy cascade. So, what happens in this energy cascade? Richardson talks about ADs, which are vertical features in the flow. So, ADs an AD would be identified by its length scale of size, let us call it L, will have a characteristic velocity is identified as U of L. We know the length scale, we know the velocity. So, what will be characteristic time scale? Let us call it tau subscript L. This would be L divided by U of L. So far so good. Now, how do we identify what we call large ADs? and how do we differentiate and we say what would be the small eddies. So, what would be the largest eddy? Can we come up with an estimate of the size of the largest eddy in the flow? In a turbulent flow. Now, there are two things which we can easily identify. Specifically, if you recall the flow through a channel or flow through the rivers, we might find the vertical structures which occupy almost the whole width or depth of the flow. So, as far as the length of this largest eddies are concerned, they would be of the same order as that of the characteristic dimension of the flow. So, the length scale of this largest eddy, let us denote it by L0. L0 would be of the same order as our characteristic length scale of the problem, capital L. How about velocity? Or what we call characteristic velocity of these large eddies or largest eddies. So, velocity scale, which we will call as UL0, can we obtain an estimate of this velocity? For that, we have to look into two parts of the turbulent flow. The flow velocity can be put as, or could be decomposed. Later on we are going to formally define that Reynolds decomposition as an average component and a fluctuating component. This fluctuating part is the one which is a feature of the turbulent flow, and we can get its root mean square value. So, the velocity scale of this eddies UL0, this is identified as that RMS of velocity fluctuations, and very often in high Reynolds number flows, this RMS value is of the same order of magnitude as our characteristic flow velocity. So, if we call this RMS fluctuation velocity as U prime, this U prime is of the same order as capital U. So, this implies that our U of L0 is of the same order as capital U. Now, how about Reynolds number linked to the largest eddy? We call it as REL0. This is defined as U0 L0 by nu, and we saw that U0 is of the same order as that of capital U, shows the characteristic velocity. L0 was of same order as our characteristic dimensions. So, this U0 L0 divided by nu, it would be roughly of the similar order as our REL. So, if REL is very large, so thus if REL is large or very large, this REL0 is also large, rather we have already seen it is of the same order of magnitude as REL0. Now, what were the observations of Richardson? His proposal was that, look, these largest eddies are the ones which carry the most of the energy in the flow. And what are the features of these largest eddies? So, features of large eddies. So, these carry most of the kinetic energy of the flow. That is one important feature. The next feature is these are unstable. Then instability is what drives the turbulent flows. So, these break up into smaller eddies to which they transfer their energy. Transferring the energy to the smaller eddies. And in fact, it does not stop at one level, it continues. So, energy is transferred from one large eddy to the next smaller one, in which it breaks up to this further smaller one to further smaller ones, and so on. So, there is what we call a cascade of energy. So, that is what Richardson termed as energy cascade. And formally we can define as energy transfer. Energy is transferred from the largest eddies to successively smaller and smaller eddies until this REL, which we have defined as UL times L by nu, becomes sufficiently small for viscosity to take over. So, that our motion becomes, for motion to become stable, and molecular viscosity becomes effective in dissipating the energy. So, what do we do? If we can think of a mental picture, let us say we have got very big or a very large scale eddies. Now, these eddies they break into smaller ones, the smaller ones they will break into further smaller pieces, and so on. And at all these scales there is a transfer of energy from one to another, until we reach at the smallest level, where the Reynolds number now here it becomes of the order 1, and at these smallest levels there is no further breakup of the eddies are fairly stable. Now, the viscosity takes over and energy is dissipated. And this is what was termed by Richardson as the energy cascade, that with their largest eddies. Now, these largest eddies they draw the energy from the mean flow and dissipate it to successively smaller eddies. Now, one thing which is very clear in those picture, that energy dissipation rate will depend on how much energy has been extracted from the flow by the largest eddies, and whatever energy is extracted, that would be dissipated at the smallest scales. So, the largest eddies, of course, that will depend on our Reynolds number. Now, let us define few more length scales. We have already defined what we call a large eddy scale or largest eddy length scale, which is very similar to or of the same order as our characteristic scale of the problem. Let us introduce yet another length scale. Let us denote it by symbol LEI, and we will say it is approximately 1 by 6 of L0. So, what is the purpose of this length scale? It is to demarcate this particular length scale, which we will call as equilibrium length scale, and this LEI demarcates the rather it provides a demarcates this large scale energy containing eddies which are anisotropic in nature from small scale eddies which can be assumed isotropic. So, there is one small very important purpose which length scale serves. It says that look, it provides sort of a demarcation that if L is less than LEI, that is the length scale, we will say these are our small scale eddies, which can be treated as isotropic, and L greater than LEI, we will call them as large eddies. They are the ones which would be primarily extracting the energy from the mean flow. Okay. Now, this L less than LEI, we will have a specific length scale range. This is referred to as universal equilibrium range. Now, let us come down to the smallest length scale. So, how can we figure out what would the smallest length scale be? The smallest length scale is the one where we say that our eddies become relatively stable for the viscosity to become dominant at that level. For viscosity to become dominant, we should have that the Reynolds number linked to the eddies should be roughly of the order 1. So, that is what we are looking at the smallest level. Now, Kolmogorov came up with the estimate of these length scales. So, these are also, that is why they are called Kolmogorov length scales, and they are defined in terms of or Kolmogorov scales, they are defined in terms of a energy dissipation. So, length scale we would use a symbol eta. Eta is defined as nu cube divided by epsilon to the power 1 by 4. Now, these estimates were derived based on the dimensional arguments. Similarly, Kolmogorov defined a velocity scale is denoted by u subscript eta. This was defined to be epsilon nu to the power 1 by 4, and the time scale linked to the smallest eddy tau eta. This was defined as nu by epsilon to the power half, and you can do a simple algebraic calculations and find out what would be the Reynolds number based on this length scale and time scale. What is the order of that Reynolds number? Now, before proceeding further, let us have a look at a few more things. The dissipation, some more estimates. Estimates of energy dissipation. This epsilon is estimated to be the order of u0 to cube divided by L0 cube, where of course our u0 and L0 represents our large just eddies. And we can easily say that eta by L0, this is of the order of Re L0 to the power minus 3 by 4, and u eta by u0, that is the ratio of the velocity length scale for the smallest eddies to the largest eddy. It is of the order of Re L0 to the power minus 1 by 4. And similarly, our time scale is tau eta by tau 0. This is of the order of Re L0 to the power minus half. Now, these scales or these relations are pertinent, very pertinent in the simulation, numerical simulation of the turbulent flows. We will see in one particular situation what we call direct numerical simulation, wherein we would like to resolve a flow at all length and time scales. So, if our length scale of the problem is of the order of L0, we can easily see our requirements that how small or how fine our mesh size should be. So, this eta gives us an estimate of the grid size which we must use if you want to resolve all scales of motion. Similarly, in time integration we have got to choose a time step which should be of the same order as tau eta, which we can estimate from our REL0. REL0, remember, it is of the same order as REL. So, if you know REL, which is very easy to estimate, RE capital L, based on that we can obtain an estimate of the time step and the grid size which we should use in our numerical simulation if we want to resolve all scales of motion. So, to summarize the discussion which we have, let us draw a diagram. Suppose this was our length scale capital L. These are energetic eddies or large just eddies L0. LEI we took as 1 by 6th of L0. So, this is the one which demarcates this energy containing eddies eddies from the small scale eddies, and the small scale eddies, they are the ones which first transfer energy from the large eddies to the small, and in the end we reach the smallest length scale which we call eta. Now dissipation starts much before eta, so let us define it another length scale. Let us call it as dissipation length scale, is roughly defined to be of the order of 60 eta, and we use the symbol L di for it. So, this is our L di. So, between LEI and LDI, this particular range is referred to as inertial range, and beyond this LDI, the length scale is smaller than LDI, this is called as our dissipation range. So, what happens here in that energy containing eddies at this length scale, the eddies will get the energy from the mean flow, Ke goes to the eddies. In inertial range, there is a transfer of energy from one length scale to another length scale. So, there is a transfer until we reach this dissipation range, and it is in this dissipation range where the energy is dissipated. And it also gives us some idea about the numerical strategies which we should adopt, and we will have a look at few of them, that what are the numerical simulation strategies which are used for turbulent flows. So, there are three approaches which have emerged for prediction of turbulent flows. The first one is what we call direct numerical simulation. Direct numerical simulation is something which is simplest one. We said, look, we are going to take the grid which is fine enough, a grid size would be the same order as that of our Kolmogorov length scale eta, time step would be the same order as Kolmogorov time scale tau eta. So, that is what we will call our direct numerical simulation. The next category is what is known as Reynolds averaged Navier-Stokes simulation, and the third one is called large eddy simulation. Now, let us have a brief look at these three strategies based on our graph which we had drawn earlier in terms of the length scales simulation strategies. We had our problem length scale capital L, now here is our L0, or LEI, LDI and eta. So, let us note down our ranges. This is the range of energetic eddies, this is our inertial range, and this was our dissipation range. So, what in effect we said in DNS, we are going to take up all the length scales up to eta. So, here resolve all length scales. So, for our grid size, if it is of the order of eta, yes, we have been able to resolve all the length scales. This is what we call direct numerical simulation. What happens in the case of large eddy simulation? Large eddy simulation says, look, we are going to resolve all these large eddies or energetic eddies. So, in fact, most of these will be resolved. We will take some of a grid size which is somewhere in between LEI and LDI, so that we are absolutely sure that all large scale eddies which contain most of the energy of the flow, they have been resolved fully. So, up to this point our flow or all the lengths are fully resolved. Below this up to our eta, this part in large eddy simulation is what we call modeled using subgrid models. And in contrast to these two, in our so called RANS simulation, what do we do? That everything is modeled. Okay. No attempt is made to resolve any of the eddy structures. So, that is how the based on this length scale, that is the division of these three simulation strategies. Let us have a brief look at some of the features of these simulation strategies. First, direct numerical simulation. So, here we are going to solve Navier-Stokes equations with extremely fine mesh. So, that our grid size is basically of the order of eta and small time steps. So, that time step is of the order of tau eta to resolve motions at all scales. So, in terms of programming effort, in terms of using a particular computational methodology, DNS represents the simplest approach from the conceptual point of view, and any of the approaches suitable for accurate time integration of Navier-Stokes equations can be used in direct numerical simulation. So, if you want to write a code, in fact the code which we would write for laminar flow, that is what can be used for a direct numerical simulation turbulent flow as well, as long as we take care of the mesh size and small time step requirement. So, nothing special is to be done in this case. Then what are the downsides here? We will have a detailed look at the downside a little later. Reynolds average simulation, here we would later on see a time averaging procedure. So, we will not solve the Navier-Stokes equation per se, but we are going to solve what we call averaged equations. There are new terms which are going to appear in governing equations which are modeled to ensure closure. That is why we saw in the previous diagram that there are lots of modeling which is used, modeling of all the eddy scales, and the modeling reduces the requirements of fine grids. Now, RANS simulations are what we call workhorse of industrial CFD for design analysis. They are the only ones which are being used from past few years for design analysis purposes in industry, and their accuracy of course would depend on the turbulence model which have been used to ensure closure. And the last one is for large eddy simulation. So, here LES resolves the largest scales of motion, that is the most energetic eddies are fully resolved while modeling the small scales of motion which we saw in the previous diagram. So, it represents a compromise between Reynolds average Navier-Stokes simulation and DNS in terms of accuracy and computational requirements. So, large eddy simulation results are less accurate compared to DNS, but their computational requirements are again much less compared to DNS, and they are far more accurate than RANS. And it is a feasible research tool for accurate simulation of large Reynolds number flows at the moment, and that is why it is slowly augmenting Reynolds average numerical simulations in industrial design analysis by those companies which can afford to have a very large scale parallel cluster. They are now using this large eddy simulation in the final design stages. For the initial design analysis, RANS is still what is being used. It is only in the final iterations people go for the large eddy simulation. Now, let us have a bit more detailed look at DNS, features of DNS. We said we are going to resolve all the scales. So, grid size is determined by the finest scale of turbulence, that is our Kolmogorov scale eta which we have defined earlier, and you can easily work out based on the definition of eta that number of grid points are proportional to Reynolds number to the power 3 by 4, where your Reynolds number we have defined its REL0, that is to say it is based on magnitude of velocity fluctuations and the integral length scale of largest eddies. And the cost of DNS scales as Reynolds number to the cube. So, that is why any increase in the Reynolds number would lead to a tremendous increase in the cost of performing a direct numerical simulation. We require in direct numerical simulation very accurate time history, and that is the reason why we can overcome the stability requirements rather easily, they are met automatically. So, explicit time integration schemes are usually preferred in direct numerical simulation. Now, please remember this the flow field which we compute from direct numerical simulation is equivalent to a single snapshot. We are doing the time stepping, and at any given time step we can have a dump of the solution that would represent a snapshot, that is what happens to our flow at a given time moment. The computational requirements are astronomical, and that is why DNS is being used primarily as a research tool to understand the mechanism of turbulence production, energy transfer and dissipation in very small domains, to understand the effect of compressibility on turbulence, to control and reduce drag on solid surfaces, wherein we can perform very controlled numerical simulation on very small solution domain, and calibrate experimental techniques for near wall flows, wherein there are lots of errors which are introduced because of the effect of the wall. They are also being used to fine tune our Reynolds averaged Navier-Stokes models and large eddy simulation models. So, that is the primary uses of the direct numerical simulation at the moment. I would also like to give you a very brief picture of just a rough estimate of the time requirements of direct numerical simulation. Now, remember these are very rough estimates, just to give you a comparative idea, and we should presume that you have got you are going to perform your simulations on a very good simulations are performed at a good parallel cluster or parallel, what we call parallel HPC facility. So, if let us have a look at let us put these things in a tabular form. Our Reynolds number, the number of grid points and the simulation time. Now, I would once again like to caution you that these are just hypothetical estimates, okay. There is nothing, they give you only an order of magnitude. So, depending on your HPC facility, the numbers were cited, they might look quite different. So, let us say if you are dealing with the Reynolds number of the order of 10 to the power 3, our typical requirements of the grid points would be 10 to the power 6, and we can perform this our simulation in, let us say, the number of hours 10. From 10 to the power 3, suppose we go to the 10 to the power 4 order of our Reynolds number. So, here our grids would be 10 to the power 8, and the time requirements will go to 10 to the power 3 hours. From 10 to the power 4, let us go to 10 to the power 5. Grid size requirement will be around 10 to the power 9, that is number of grid points which we need, and we would need, you will be surprised to know that we would require not in hours, but few years. 10 to the power 6. So, typical industrial scale Reynolds number. We require the number of grid points the order of 10 to the power 13, and the solution time would go into few thousand years. Of course, this 1000 years might depend on, they might be reduced to, let us say, even if you let us say 100 years, that tells you about the impossibility of carrying out a direct numerical simulation for our industrial flow problems. So, we cannot use direct numerical simulation to let us simulate at all the length scales the flow around a racing car or a flow around an aircraft. That is next to impossible unless there is a breakthrough in the computing technology and the algorithms which can give us very fast numerical simulations. Now, we will introduce one particular terminology before we finish today, which relates to our Reynolds average Navier-Stokes simulations. So, this is what we call Reynolds decomposition. So, Osborne-Reynolds suggested that a flow variable at a given spatial point at a given instant can be represented as the sum of mean value and a random fluctuation about this mean value, and this decomposition is referred to as Reynolds decomposition, and the process of obtaining the average value which is used in this decomposition, that is referred to as Reynolds averaging. There are many things which are looked. We are going to have a detailed look at how do we decompose or define our Reynolds decomposition for any flow variable. We will have a look at the Reynolds averaging for statistically steady flow and statistically unsteady flow, that the slight difference the way we would define our averaging process for the two cases. And we will also have a look at the properties of the algebra of averages in Reynolds decomposition, because these will be useful in obtaining the Reynolds average Navier-Stokes equations for RANS simulations. But this we are going to take up in the next lecture. For this lecture we would stop here. If you are interested, there are few references listed here for turbulent flows. There are many books. The two most popular books listed here: Lec-01 in 2008 named Turbulence, and another one by Pope published in 2000 on turbulent flows. Numerical simulation on turbulent flows of CFD books which we have already seen earlier. You can look at the book by Chung, Computational Fluid Dynamics, or book by Ziger and Perek, and the book by Versteeg and Maralasekara. This book is specifically relevant for the details about different RANS simulation models.